Good afternoon, everyone. My name is Ismael. I know many of you here, and we've had great conversations. And for those of you who don't know me, I'm one of the co-founders of Lagrange. So we are an early-stage company that focuses on ZK coprocessing, among other things. And so how does our infrastructure work? What is a ZK coprocessor, and what makes our approach to zero knowledge interesting? Well, we'll walk through all of those today in some detail. So the title of this talk is Giving a Verifiable Database to Every Smart Contract. And so, shameless plug, we have a coprocessor. The first testnet we're calling Euclid, Lagrange Euclid. It's a fun name. That's on testnet right now, and we'll have a future iteration of this in about 4 to 6 weeks, expanding the functionality of the next iteration. We'll call that V1 testnet, maybe V0.5. And so we'll talk about Euclid a bit today and also talk about the scope of our upcoming testnet. So what makes our approach to ZK coprocessing and ZK proving very broadly interesting? So we have a very specific belief on how you can scale computation over blockchain data in a meaningful way. And that is through pre-processing. To be able to take the concept of extracting data from a blockchain and separate that from the concept of computing over that data. And so with our proving network and our coprocessor, it really breaks down this question into 2 steps. The first is pre-processing. So how do we take, let's say, a series of data from within a smart contract, so some predefined storage slots, over some period of time, and how do we prove that there exists a new structure built in a ZK-friendly way that contains the same subset of elements, right? So take all of this hairy MPT data that's linked over 10,000 blocks and prove that there's a simple binary Poseidon 2 Merkle tree containing the same leaves. And then how do we prove general purpose SQL-like computation over that new tree such that at the end, you can prove both the origin and the query over that data within a single proof. So pre-processing. You think about blockchain data, it's typically, for EVM chains, very hairy to compute over. MPT tree, RLP encodings, Keccak hash functions, all of these things typically increase the time it requires to compute. Moreover, the chronology of how blocks are linked means that introspecting its historical state has an amount of computation proportionally to the historical depth, proportionate to the historical depth. So if you wanted to go back 10,000 blocks, you could really only prove that through doing greater than 10,000 hash functions. And that's a limitation on computation, it's a limitation on queries. So pre-processing is, well, how do we take all of this data that we can prove exists in a commitment, and how do we prove it's equivalent to a new structure? And then how do we update that proof of equivalence, this new structure that updates, such that we can always serve queries cheaply and efficiently over some processed and transformed data source? The second is query. So how do we take that transformed data source, let's say all Uniswap v3 swap events over the last 10,000 blocks, so let's say all storage slots of curve prices. And how do we structure something over that that is meaningful? How do we say I want to access 10,000, 20,000, a million slots, 2 million slots, and have a computation that can return a result that can be interpreted by a smart contract and consumed? So the simple way of thinking of what this can do is, well, what can you do in Dune? What would you use Dune for? What would you price in Dune? What kind of rewards programs would you build in Dune? Maybe grants programs? All of the things you could build in SQL using on-chain data today, we let you take that and verifiably consume that in your contracts. So you can take this pre-transformed structure, you can run a computation and prove the computation in parallel across a series of nodes, and you can compose and recursively combine those together into a proof that you can then verify back on chain. And so currently, the way this works is, in order to define a data set in your contract, you emit an event that notifies our network approvers that you want some subset of data in that contract stored. It's like basically indexing. And then we generate a proof of the equivalence of that index data with this optimized structure. Then you can very simply emit another event indicating you want to generate a proof of a query over that data. And so First contract that we did was obviously pudgy penguins, because why not? And we can run queries over about 1 million storage slots in about 1 minute 20 seconds in a proof. So we can prove that we've correctly extracted 1 million storage slots over some block range, and that we've computed some select query over that. And so you can think of defining this data structure on chain, very simple, like any standard. If you want to define that over a mapping, what you effectively need is to define the length of the mapping in memory so that we can access that, as well as let's say the address or the primitive types you want. And then we can construct these proofs of the equivalence and then support queries over them. Simple event, you can register your contract to be indexed by the network and have the equivalence proofs generated to the index data. Then querying. The way we have defined our on-chain interface for querying, and this is obviously subject to change, is we have events that correspond to specific SQL statements, wherein the parameters of those events are malleable. So you can, in fact, put in different variables into those, for example, select query, or select based on address by having the parameter in the event be the address. And then the network will generate these proofs asynchronously, and we'll verify them back on chain within some SLA. And we very soon will have full general purpose SQL. There's a new paper that our team has come up with, Perseus, which is full general purpose SQL based on AST parsing that will support things like joins, unions, and some more complicated SQL primitives that would otherwise be quite difficult in prior art and prior literature. And so our database, you can think of this type of proving as very horizontally scalable. And one of the principles that this has is the concept of updatability. And this is how we're able to scale this computation in a meaningful way. So typically, when you think of a proof or a batch proof over the computation of blockchain data, these proofs are not updatable. And so if I wanted to compute between block B and B plus K, some large computation, and then I wanted to refresh that computation between B plus 1 and B plus K plus 1, you would have to recompute from scratch. You'd have to go back through the state, you'd have to compute over all the inclusion, and then you'd have to regenerate whatever the computation is over that data. What you get with this is the ability to update, thanks to a vector commitment that our team has proposed called RECL trees. And so what makes RECL trees special is that RECL trees are a batch proof that can be constructed from any recursive snark or folding scheme that is updatable in logarithmic time proportionate to the change in the data that's being computed over. Which means we can define very large equivalence proofs over very large subsets of this index blockchain data that we can then update to prove that the indexing is correct over some future iteration of that chain. So if you think of Ethereum, where let's say the entropy of state has a frequency of every 12 seconds, you need to be able to have a computation over data that is also updatable within 12 seconds. Otherwise, there's no way you can effectively create a table structure that can maintain that type of equivalence proof. And so this is what we're able to do with RECL trees, where we're able to update our proofs of any map-reduced computation proportionate to the change of the underlying data that's being computed over. And so you can think of the way this works as basically defining, we call this canonical hashing, you see the cursor actually? Yeah. You define a representation of the data that is anchored at every branch node. And then when something changes, all you do is you update the portions of the tree that have changed based on the alteration of state. And that means that the majority of the branch nodes obviously don't change, so you don't have to actually update the majority of the computation. Then you just recompose together any of the branches that have changed. Another thing that we're doing in this is this concept of digest translation. And so digest translation is something that our team has proposed. This is, I believe, also referred to as order agnostic hashing or multi-set hashing is the other term for it, where you want to prove that there are two data structures that potentially have different arities that contain the same subset of leaves. And you can do that through, in essence, hashing together these elements in a way that does not that can prove, you can use an accumulator that hashes them together in a way that is agnostic to their order. And we can do this, and we can, within our rectal trees, we can change the arity of the underlying data structures we're computing over. And putting this all together, we can effectively define these like ZK database or provably equivalent data structures over MPT data. And then we can structure computation over that by paying a one-time indexing cost with a cheap amortized query cost. And so for some context, we did last week about 20,000 queries over L1 data. And that was at about maybe 5-ish to 10-ish cents in query and verification cost, and very little query cost in terms of computation, because we were able to obviously amortize that with the one-time basically indexing and digest equivalence cost. And so the way this scales is really through like a MapReduce style framework, where we're able to parallelize most of the work across a series of distributed workers. And then we're able to recursively concatenate both the data and the proofs of the correct computation of that data back together across our network. The first version of our network was deployed in a centralized context in our backend, but we have a version that's deployed decentralized that will be out in about 2 weeks. And so what this lets you do is you're able to scale horizontally by just throwing more workers at the problem. And you can, because of the naturally parallelizable nature of the construction, reach performance times that are a lot better than what you would otherwise be able to do if you were doing everything sequentially. And so query performance, the asymptotics for about 1 million storage slots of computation are about 9 seconds. In our current implementation, obviously, we're bottlenecked by latency and messaging complexity, so it's about a minute for over about 1 million storage slots. But obviously, as we throw more parallelization at this, it'll go faster. And for some context, if you look at like other storage inclusion-proof solutions, you're typically talking about like 30 seconds per proof of inclusion, and so that's obviously a lot slower. Maybe you can even talk about using something that's a little bit better built, like some of the new ZK VMs, you might be talking like 10-ish seconds per slot. But to do 1 million slots in about a minute requires a very specialized system. That's one of the benefits you get from this. All right, so that concludes the talk today. So any questions?